right, hi folks, this is Larry Mussolino. I'm recording a part 3 video for the Module 5 MyLab's homework. And so be sure to check out course announcements for a part 1 video and a part 2 video. But there was a few other examples that I wanted to include. And so let me start here with number 16. This one says use logarithmic differentiation to find dy dx. So what is log differentiation asking you to do? Well, it's a little bit of a shortcut to find derivatives for messy functions. And the idea is going to be to take ln of both sides first before taking derivatives. Then take the derivative of both sides. You might say, what's the point of this? Well, by using properties of logs, you can sometimes make an expression easier to differentiate. Let me remind you about a couple of properties of logs before we get started here. There's a property that says if you're taking the log of x times y, you can break this up to an addition. It would be ln x plus ln y. How about ln of x over y? This is ln x minus ln y. And one more, what if you have ln of x to some exponent r, call it? This property says you can bring r down in front as a multiplier and write it as r times ln x. So these are properties of logs that we can use to help us with this log differentiation. All right, let me write down the equation they have. Y equals square root x plus 7. All right, well, one thing I can do here is instead of writing this as square root, the square root can be written as exponent 1/2. So I'm going to write that. But now I'm going to take ln of both sides. All right, this is going to be ln y equals ln of x plus 7 to the 1/2. All right, let me use this property that says you can bring the 1/2 down in front. That's this property right here. So I can write this here as 1/2 ln x plus y, x plus 7. But now I'm going to use this property that says if you have a multiplication, you can rewrite it as the addition of the ln. So I'm going to write this as 1/2 ln x plus 1/2 ln x plus 7. Because this 1/2 is multiplying this whole expression here. And this is all equal to ln y. Now I'm going to take the derivative of both sides. And because now notice this right-hand side is it's an addition expression. So it's going to be simpler to take the derivative of this right-hand side than taking the derivative of this messy square root up here. All right, let's take derivative both sides then. The derivative of ln y, well, that's 1 over y dy dx. Remember, when you take the derivative of y, you have to include a dy dx as the chain rule. All right, let me come over to the right-hand side now. The derivative of ln x is 1 over x. And the derivative of ln x plus 7 is 1 over x plus 7. All right, let me multiply both sides of this equation by y, because I want to get dy dx by itself, because that's the answer format I'm looking for. So I'm going to multiply both sides of this equation by y. So I'm going to end up with dy dx equals y. I'm going to factor out this 2 from the denominator and make it y over 2. And then I have 1 over x plus 1 over x plus 7. All right, now I'm going to do a little bit of algebra because I want to add these two fractions together. And to do that, I can get a common denominator. So to do that, I'm going to multiply. Let me erase this here for a little more space. What I'm going to do is multiply by x times x plus 7 over x times x plus 7. I'm allowed to do that because this fraction is equal to 1. And I'm trying to form a common denominator here. The LCD I'm going to look for is x times x plus 7. All right, let me do this multiplication to the first parenthesis. That's going to get me x plus 7 over x times x plus 7. And now I'm going to multiply to the second fraction. That's going to get me x over x times x plus 7. Now I can add these fractions because they have the same denominators. So that's going to get me dy dx. Let me erase some more of this stuff down here for a little more space. All right, dy dx is y over 2. And I'm adding top. It's going to be 2x plus 7 over x plus 7. All right, but I can replace the y with the square root of x plus y. So I'm going to do that. So it's the square root of x plus 7 times 2x plus 7 over 2x plus 7. There's one other simplifying that I can do here because I have a square root of x plus 7, and in the denominator here I have an x plus 7. So this square root would actually cancel out with the factor on the bottom, leaving me, let me write the final answer here, leaving me an x plus 7. And so I think I could just leave the answer like that. So again, this idea of log differentiation, take the log of both sides, that's what we did here. Use log properties to simplify the right-hand side, that's what we did here. Now you can take the derivative of both sides. All right, that was number 16. How about if we look at another example? How about we come here to number 18? All right, so this one is saying y equals ln of this fraction, and they're asking us to find the derivative. All right, well, for this, I want to remind myself of how do you find the derivative of an ln kind of function? So ln of f of x. Well, the derivative here is where you set up a fraction. In the denominator, you put this f of x function here that's in the parentheses, and on the top, you put the derivative of that function on top like that. All right, so let's set up our example. Here is our function. Let me circle here what we're calling f. We're calling f this function right here. So the way I'm going to set this up is I'm going to put the function on the bottom and its derivative on the top. Well, the bottom is just copying that function as is. So it's going to be e to the 2 theta over 1 plus e to the 2 theta. But let me find f prime, because that's going to be a little tricky. F prime, I need the quotient rule. So in this example, f is 1 plus e. F is e to the 2 theta over 1 plus e to the 2 theta. I want to find the derivative. So I'm going to need the quotient rule. The quotient rule says, and usually for the quotient rule, the way I set this up is I label the top as f, the bottom is g. Let me call this function here h to avoid a little confusion. So I'm going to call this h prime. All right, well, the quotient rule says take g times f prime minus f times g prime all over g squared. This is the quotient rule. All right, let me plug in here. So we need the g function, that's the bottom, that's 1 plus e to the 2 theta. times the f function, that's the top, e to the 2 theta, minus the f function, that's e to the 2 theta, times the derivative of the bottom. Well, the derivative of the bottom is going to be e to the 2 theta times 2. Okay. I'm sorry, I made a mistake here. This should be g times f prime. So for f prime, let me write it up here to make it a little easier. F. You know what I'm realizing is I might be confusing things by calling too much stuff here f. Let me do this. Let me back up a little bit, and let me do this. Let me start over again with the quotient rule, because I think I might be confusing people. So I'm going to call this inside parenthesis the f function. When you want to find the derivative of ln of f of x, you set it up like this. You put that function in the parenthesis on the bottom and its derivative on top. So we put that function itself on the bottom. Now we need the derivative. All right, how about f prime? Well, let me write down the quotient rule. The quotient rule says take the bottom of the expression times the derivative of the top, all right, that is top prime, minus the top times the derivative of the bottom, all over the bottom squared. Maybe that's an easier way to write it. So for us, the top is e to the 2 theta. So here is our, let me write down f of x here. Our f function was e to the 2 theta over 1 plus e to the 2 theta. So I'm calling this the top of the fraction, and I'm calling this the bottom. All right, so let me plug in here. The bottom is 1 plus e to the 2 theta. The derivative of the top is e to the 2 theta times 2. Right, I'm using the chain rule for that. Now I need the top, which is e to the 2 theta, times the derivative of the bottom, which is e to the 2 theta times 2. All over the bottom squared, which is 1 plus e to the 2 theta squared. All right, let me try to clean this up. This is 2 e to the 2 theta multiplying 1. And now this is 2 e to the 2 theta multiplying e to the 2 theta. So I think I can write that as e to the 4 theta. Minus 2, this is e to the 4 theta. Over 1 plus e to the 2 theta squared. All right, it looks like on top I can do some canceling. So I got 2 e to the 4 theta minus 2 e to the 4 theta, cancel those. So I'm left here with 2 e to the 2 theta over 1 plus e to the 2 theta squared. Remember, this is the derivative function, the derivative of what was inside this parenthesis. Well, that belongs on the top of this fraction. So it's going to be 2 e to the 2 theta over 1 plus e to the 2 theta squared. Well, let me take this fraction, this division of two fractions, and I'm going to leave the top alone. But when you divide two fractions like this, you take the bottom fraction and flip it, and then multiply. So I'm flipping this bottom fraction upside down. Now I see some canceling I could do here. There's an e to the 2 theta top and bottom, so I'll cancel that out. And there's a 1 plus e to the 2 theta top and bottom that I can cancel out. So what I'm left with is 2 over 1 plus e to the 2 theta. So I think this is going to be the final answer for this one. All right, so this was a little messy, but what you had to know for this one is if you have a starting function of y equals ln of some function, I called it f of x, the way you set up the derivative is create a fraction. The bottom of the fraction is the function itself that was in the parenthesis. The top is the derivative of that function. All right, that's the derivative of a ln function. All right, let me see if there's one more we could do here. Maybe let's do one involving some trig functions. And it looks like this one is a fraction. So we're going to need the quotient rule for this one, for the derivative. Let me write the quotient rule the same way I wrote it a minute ago. To find dy dx, we're going to take the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. All right, let's plug in here. Our top function looks like it's 2 cosine x. Then the derivative of that is 2, derivative cosine is negative sine x. So I'll write that as negative 2 sine x. All right, our bottom function was 1 minus sine x. So the derivative of that, the derivative of sine is just cosine. All right, let's plug in then to this quotient rule. So for dy dx, we need the bottom. That was 1 minus sine x times the derivative of the top. That was negative 2 sine x. All right, let me come back here. Now we need the top. That was 2 cosine x times the derivative of the bottom. This should say derivative of bottom, which is just a cosine x. All over the bottom squared. 1 minus sine x squared. All right, let's do some cleanup here. So dy dx is, I'm going to take this negative 2 sine x and multiply it inside the parentheses. So it's going to be negative 2 sine x plus 2 sine squared x. And in the back, it looks like I have a negative 2 cosine squared. All right. Well, let me pull out a 2 here. Actually, let me factor out a negative 2. Oh, I'm sorry. Let me put this all over 1 minus sine x squared. So this is going to be negative 2 sine x minus 2 sine squared plus cosine squared. All over 1 minus sine x squared. But this parenthesis back here, sine squared plus cosine squared, you remember that as a famous trig identity. That's equal to 1. So what we're left with is negative 2 sine x minus 2 over 1 minus sine x squared. All right, let me factor out a 2 from this. Let me factor out a negative 2. And we'll see if anything cancels out here. Let me make a little more space. Let me, folks, I just realized I made a small sign mistake. Let me go back and fix something. If you notice up here, the bottom of the fraction was 1 minus sine x. I should have written the derivative as negative cosine x, because the derivative of negative sine is negative cosine. So this derivative of the bottom should have been a negative cosine here. That would make this a plus 2 here. So that makes this a plus 2 here. All right, so that means we have a plus 2 here. All right, now let me just rewrite the numerator to make it a little easier to see. Let me rewrite the numerator as I'm just going to flip the order here. So I'm just going to write it as 2 minus 2 sine x. Because now I think it's a little easier to see that you can factor out a 2 from the top, and it's 1 minus sine x left over. But I'm noticing that 1 minus sine x on top will cancel with one of the 1 minus sine x is on the bottom. Final answer here is dy dx is 2 over 1 minus sine x. So folks, the key here is making use of the quotient rule. The quotient rule is written out down here. As you work through this problem, you're going to come across the famous identity that says sine squared plus cosine squared. Remember, that is equal to 1. And that's going to help you simplify this final derivative. All right, hope that's helpful as you're working here in the Module 5 homework, folks. Thank you.